In the mid-1940s, as the Second World War intensified, Britain faced a sharp technical dilemma. The Navy needed small, fast vessels capable of striking hard and escaping quickly. Aviation gasoline engines were light and powerful, but dangerously prone to fire. Diesel engines were far safer, yet too heavy and too slow for this role. The question was no longer how to refine existing designs, but whether the entire concept of a diesel engine could be reimagined. In that moment, Napier, a long-established British engine builder, chose a radical path. They accepted complexity and extreme engineering as the cost of performance. From that decision, the Napier Deltic began to emerge, not as a compromise, but as a bold, technical statement shaped by war. The core inspiration behind the Napier Deltic did not come from Britain, but from Germany, where pre-war engine design thinking was already far ahead of its time. During the 1930s, Junkers developed two-stroke aircraft diesel engines using opposed pistons, a bold solution aimed at breaking the limits of conventional diesel design. This layout completely eliminated cylinder heads and valve gear, sharply reducing weight, the number of moving parts, and mechanical losses. Instead of a single piston compressing the charge against a cylinder head, two pistons moved toward each other from opposite ends of the cylinder, creating pressure at the center. This allowed more efficient combustion and enabled much higher engine speeds, something rarely associated with diesel engines of that era. Thanks to a layout that was geometrically simple but extremely demanding to manufacture, engines such as the UMO 204 and UMO 205 achieved exceptional power-to-weight ratios along with very low fuel consumption. The trade-off was precision. These engines required extremely accurate machining and perfectly synchronized piston motion. Even minor deviations could lead to thermal imbalance or serious mechanical failure. This sensitivity explains why opposed piston designs struggled to gain acceptance in civil aviation, an industry that valued ease of maintenance and long-term reliability over experimental performance. Napier recognized the strategic potential of this technology and acquired a license to develop it further, resulting in the Culverin engine. From a technical standpoint, the Culverin was a significant step forward. It was compact, fuel-efficient, and far safer than gasoline engines. In peacetime, however, it was judged too unconventional and poorly aligned with prevailing operational practices in aviation. What appeared to be a dead end changed completely with the outbreak of war. When the Royal Navy began searching for a high-speed, lightweight, and powerful diesel engine for small combat vessels, the Culverin suddenly became a valuable foundation for an entirely new direction in engine development. Napier did not stop at a single opposed piston engine. They asked a further question. What would happen if several of these engines were combined into one? The result was a structure unlike anything that had existed before. Three banks of cylinders were arranged in a triangular layout. Each side of the triangle formed an opposed piston bank, and each corner housed its own crankshaft. These three crankshafts did not operate independently, but were linked through a system of synchronizing gears that combined their output into a single central drive shaft. This shape recalled the Greek letter delta, and from it, the name Deltic was born. It was an 18-cylinder, two-stroke engine with no cylinder heads, no valves, and virtually no mechanical pause in its operating cycle. Everything happened continuously, rapidly, and under constant mechanical tension. Napier Deltic achieved something that most diesel engines of its era simply could not. It delivered an extraordinary level of power relative to its size and weight. The standard 18-cylinder configuration produced around 1,650 horsepower, while later turbocharged variants pushed output beyond 3,700 horsepower. Even more remarkable was how that power was delivered. The engine operated at rotational speeds of up to 1,500 revolutions per minute, an exceptionally high figure for a large displacement diesel engine of the time. This performance came at a cost. The Deltic's two-stroke cycle meant combustion events occurred almost continuously, with no meaningful pauses for mechanical or thermal recovery. Combustion density within each rotation was extremely high, subjecting pistons, bearings, and crankshafts to relentless thermal and mechanical stress. The three crankshafts, locked together through a complex synchronization gear train, operated under constant load. As engine speed increased, the gear system produced a distinctive metallic resonance, a deep, sharp mechanical growl that intensified with every rise in RPM. What made the Deltic extraordinary also made it unforgiving. It was not an engine designed for gentle operation or long idle periods. It demanded precision, discipline, and constant attention. In return, it delivered performance that redefined what a diesel engine was capable of achieving in the mid-20th century. The phase synchronization gear system produced a distinctive hum that rose steadily with engine speed. At maximum output, however, it became extremely loud enough that large acoustic shields were required to keep noise levels within acceptable limits. The naturally aspirated 18-cylinder versions relied on mechanically driven scavenging, using large blowers to push air through the cylinders and clear exhaust gases. This system was essential to the engine's efficiency and high power output. The Deltic was designed from the outset for motor torpedo boats and fast attack craft. By 1952, 6 engines had been completed and prepared for extended endurance trials. One of the earliest tests used a captured German E-boat. The choice was deliberate. These vessels were originally powered by Mercedes-Benz engines of comparable output, providing a reliable point of comparison. 2 of the 3 original engines were replaced with Deltic units, and the results were immediately apparent. The Deltic engines were significantly smaller and dramatically lighter. Each Deltic weighed roughly 1/5 as much as the Mercedes engines it replaced. This weight advantage quickly made it the preferred power plant for small, high-speed naval vessels, including the Royal Navy's Dark-class fast attack craft. Built largely from aluminum, the engines also had a low magnetic signature and relatively low vibration, both valuable traits in naval service. As a result, Deltic engines were widely adopted for mine countermeasure vessels, including the Royal Navy's Ton and Hunt-class minesweepers. The Deltic also found use beyond Britain. Norwegian Nasty-class patrol boats were equipped with these engines and later sold to Germany, Greece, and the United States Navy. During the Vietnam War, American forces used these boats in covert operations, where the engine's steady mechanical hum was considered an advantage rather than a liability. Unlike many engines we are familiar with today, the Deltic was not truly small, even though it was more compact than conventional 4-stroke diesel engines of comparable power. Standing beside it, one quickly understands its scale. Period photographs often show a technician working on the phase synchronization gearbox, providing a clear sense of size. That gearbox also illustrates one of the engine's most remarkable features: a complex gear train that combined the output of 3 separate crankshafts into a single central driveshaft. In 1956, the Royal Navy explored an even more ambitious concept. A twin-turbocharged Deltic was proposed, and a prototype was built, not as a conventional engine, but as a gas generator within a compound gas turbine system. In this configuration, the Deltic did not drive the propeller directly. Instead, it produced high-energy exhaust gases that fed a turbine housed within a combustion chamber. The turbine system was designed for an output of 6,000 horsepower. However, as engineers familiar with the project had anticipated, mechanical limits were reached before that figure could be sustained. At approximately 5,600 horsepower, the engine suffered connecting rod failure, confirming concerns about the extreme stresses involved. As gas turbine technology advanced rapidly in the following years, the concept of a compound Deltic turbine was ultimately abandoned. Pure gas turbines offered greater reliability and development potential, even if the combined system promised higher theoretical efficiency. In the end, simplicity and durability outweighed experimental gains, and the hybrid Deltic concept quietly faded into history. By the late 1950s, Britain's railways were entering a period of change that was nothing short of critical. Steam locomotives were still powerful and reliable, but they demanded enormous preparation time, from lighting fires and taking on fuel to extensive cleaning and servicing after every run. As operational demands increased, British Rail committed to dieselizing the network. Almost immediately, however, a major problem became clear. The diesel locomotives then available were simply not powerful enough to replace the high-speed steam engines on the East Coast Main Line, where long-distance trains ran at sustained high intensity for hours at a time. The Napier Deltic arrived at exactly the right moment, offering what was nearly a unique solution. From the original prototype, British Rail developed the Class 23 in 1959, followed by the introduction of the Class 55 between 1961 and 1962. Although widely known as the Baby Deltic and the Deltic, these locomotives represented a completely new operational philosophy. In total, 22 Class 55 locomotives entered service, replacing 55 steam engines, including iconic Pacific types and even the A4 Mallard, the fastest steam locomotive in the world. The Class 23 Baby Deltic used a single 9-cylinder turbocharged Deltic engine, producing approximately 1,100 horsepower. The Class 55, by contrast, was fitted with two 18-cylinder mechanically blown Deltic engines, each rated at 1,680 horsepower. With a combined output of more than 3,300 horsepower, the Class 55 became one of the most powerful and fastest diesel locomotives in the world at the time. The decision to use two moderately rated engines rather than a single high-output unit was deliberate, intended to extend engine life and reduce stress on individual power plants. In service, the Class 55 could haul 13 coaches from London to Edinburgh at an average speed close to 100 miles per hour, reaching over 114 miles per hour on level track and even higher speeds on downhill sections. With no need for fire lighting or ash cleaning, these locomotives were almost always ready for duty. British Rail also adopted a high availability philosophy for the first time, allowing complete engine swaps within a single day if a failure occurred, rather than weeks of on-site repair. For a brief but memorable period, the Deltic became a symbol of speed, power, and modernity on Britain's railways, until that era came to an end with the arrival of the Intercity 125 in the late 1970s. The Deltic's shortcomings only truly revealed themselves when the engine was removed from the environment it had been designed to inhabit. In naval service, the Deltic worked in relatively open machinery spaces, often with direct airflow and far fewer hard surfaces to trap sound. Noise and vibration, while still severe, were able to disperse outward rather than reflecting back toward the crew. On a railway locomotive, the conditions were fundamentally different. Two Deltic engines were installed inside a tightly enclosed steel body, surrounded by rigid panels and structural members. There was very little volume for sound to escape, and almost no opportunity for it to dissipate naturally. As a result, the acoustic energy produced by the engines behaved very differently. Instead of fading away, it bounced repeatedly off the steel walls of the engine room, reinforcing itself and building into a constant, oppressive presence. The driving cab was only a few meters from the engines, separated by insulation, but not by distance. Crews were expected to work in this environment for 5 to 6 hours at a time, often at sustained high power. What might have been tolerable in short naval duty cycles became exhausting and potentially damaging when experienced continuously on long railway runs. British Rail understood this risk from the beginning and attempted to address it systematically. Sound insulation was built into the locomotives from new, and further layers of acoustic material were added as experience accumulated in service. Measurements were taken, modifications were trialed, and the design was refined wherever possible. However, the underlying engineering reality of the Deltic could not be escaped. The engine operated at rotational speeds far higher than those of conventional railway diesels, and its two-stroke cycle produced an exceptionally dense pattern of combustion events. This created a sharp, complex sound spectrum that insulation could soften but never truly suppress. Even after extensive improvements, cab noise levels typically remained between roughly 83 and over 100 decibels, well above modern thresholds for safe long-term exposure. Ear protection was no longer a precaution but a requirement, particularly whenever crew members had to enter the engine room during operation. The effect was even more dramatic in the large stations of the East Coast Main Line. Victorian-era train sheds, built from iron and glass, acted like enormous resonant chambers. A Deltic idling at the platform could overwhelm the public address system. When the driver applied power to depart, the sound did not simply follow the train out of the station. It lingered, rolling back and forth under the roof for minutes, echoing in a way that no other diesel locomotive could reproduce. Crucially, this was never an intentional display of power. The Deltic was not designed to dominate railway spaces. It was a naval engine, created for short bursts of extreme output at sea, now operating in a confined environment it had never been meant to endure. Perhaps the most unconventional proof of the Deltic engine's power did not appear on rails or at sea, but in the heart of New York City, in the form of a firefighting machine unlike anything seen before. This was the New York City Fire Department's super pumper, a central pumping unit that formed the core of a 5-vehicle system consisting of the main pump truck, a hose supply vehicle, and 3 satellite water distribution trucks. The idea of a land-based fireboat had existed for decades. In 1910, naval architect William Gibbs proposed a vehicle capable of delivering water volumes comparable to a fireboat, but mounted on a truck chassis so it could operate deep within a city. For more than 50 years, the concept remained theoretical. No engine available at the time combined the compact size and immense power required for such a machine. That changed in the early 1960s with the arrival of the Napier Deltic. In 1962, the Napier Deltic T1837C engine, producing roughly 2,220 horsepower, was selected to drive a 6-stage de Laval centrifugal pump. The following year, after a massive fire on Staten Island exposed the limits of conventional firefighting infrastructure, the FDNY moved forward with the project. Mack Trucks was commissioned to build the super pumper to Gibbs' concept at a cost of $875,000, an extraordinary figure for the era. The super pumper was designed to handle fires on a scale beyond anything standard equipment could manage. It could draw water simultaneously from up to 8 hydrants, or directly from rivers and the harbor, then deliver flows of up to 10,000 gallons per minute at low pressure, or about 8,800 gallons per minute at 350 pounds per square inch. Its primary 8-inch monitor was capable of projecting a solid stream of water as far as 600 feet, including straight upward to supply high-rise firefighting operations. At full output, the Deltic engine consumed fuel at a remarkable rate, exceeding 2 gallons per minute during major incidents. Between 1965 and 1982, the super pumper responded to more than 2,200 calls, supporting some of the largest fires ever fought across all 5 boroughs. Its service life ended not because it lacked capability, but because New York City's financial crisis made the cost of operating and maintaining such a specialized machine impossible to justify. However, the Deltic's fundamental technical limitations soon became apparent in ways that went far beyond noise alone. Engineers often described the Deltic engine as temperamental, not because it lacked strength or reliability, but because it demanded extremely precise operation and a very high level of professional maintenance. To keep all 22 locomotives available for service, British Rail had to maintain a large pool of spare engines at Doncaster and rely on rapid engine replacement rather than conventional in-situ repairs. This system worked only while English Electric's accumulated expertise remained closely involved. When British Rail assumed full responsibility for maintenance in 1970, contemporary records show that problems emerged almost immediately. Within a year, reports indicate that at times nearly half of the fleet was out of service simultaneously. Cracking of cylinder liners, once an occasional issue, increased sharply, while workshops designed for standard railway equipment struggled to meet the naval-grade precision the Deltic required. Exhaust fires caused by oil accumulation, structural cracking in coaches subjected to daily operation at around 100 miles per hour, and later corrosion and fractures in the locomotive bodies themselves all raised serious questions about long-term viability. In the end, the Deltics were judged too noisy, too complex, and too expensive to maintain compared with the machines that eventually replaced them on the East Coast Main Line. The Napier Deltic was not a failure. At sea, it was a masterpiece, a compact and immensely powerful engine perfectly suited to the harsh demands of naval warfare. On the rails, it became something very different, an extraordinary machine that delivered unmatched performance, yet one that was ultimately unforgiving to the people who had to operate and maintain it every day. The story of the Deltic is a reminder that technical brilliance does not exist in isolation. Engineering success is not defined by power or innovation alone, but by how well a design fits its operating environment. A machine can be revolutionary in one context and problematic in another. The Deltic teaches a lasting lesson that the right technology, placed in the wrong setting, can lose its advantage, while the same design, used as intended, can achieve greatness.